Hello everyone, my name is Jose Figueroa and today I'm going to be introducing Group 8. Our project is based off of helping the visual impaired using artificial intelligence object detection while reducing light distortion. The group is made up of myself, Frankie, Enrique, and Eduardo. A quick summary about our project. Our project aims to help CSUB students who are visually impaired by using modern technology to assist them in avoiding any objects that could cause harm. To accomplish this, we developed an algorithm that works with YOLO v5 architecture that helps support our main goal, as well as implementing various hardware components to use with our algorithm. As for our dataset is created with objects found in CSUB. The dataset includes objects such as vehicles, stairs, traffic signs, and much more. To help improve accuracy, we trained the algorithm with images taken during the day and late afternoon. We captured multiple copies of each image and made changes to them. For example, flipping, mirroring, and placing a filter over the image allows the object detection algorithm to have a better chance of identifying objects with greater accuracy.
Hello everyone, my name is Enrique Tapia. Today I will be talking to you about how our project works. In our project, we use YOLO v5, which is a state-of-the-art object detection algorithm that has become the main method of object detection in computer vision. In our project, we created and trained a custom dataset that is comprised of objects located at the CSUB campus. The algorithm works by detecting objects in real time, and when the user is approaching these objects or the objects are approaching the user, it will run a threat analysis to determine if the user needs to be notified via a text-to-speech notification. Here you will see two pictures. On the left-hand side is a simple overview of how we were able to capture the distance of an object relative to the user. By using two cameras and then analyzing where the object sits on both frames, we were able to do some math to determine how far the object is. On the right side, there is a simplified overview of our project. We start with the hardware, and then we move on to the object detection and identification. Here, any object that is identified will be given a unique ID. From there on, the object will have its history stored. This means that anywhere the object is moving to, its history will be recorded. From there on, a prediction of where the object will appear next is made and then sent back to the object detection. This is used to make sure that the object keeps the same ID throughout the whole entire process. Next, we capture the object's distance. From there on, we will do a threat analysis to determine whether the user needs to be notified or not. So what does our algorithm consist of? Well, our algorithm is responsible for handling the various hardware components, along with processing and analyzing each object that is detected. For each object that is detected, the algorithm assigns a unique ID and stores its location history. The algorithm then analyzes the object's history and applies the Kalman filter to predict the location of the object in the next frame. It will then capture the object's distance and run a threat analysis to determine whether or not to notify the user.
Voice recognition / TTS. The main objective of voice recognition and text-to-speech was to create an interactive and hands-free experience for the user. The voice recognition will allow the user to ask our project to look for specific objects by invoking a wake work to activate the system. The text-to-speech gives the user feedback and notifies the user of any potential hazards that may cause harm.
Now turning to the hardware section of our project supports the combination of various hardware configurations and arrangements, such as the use of one or two cameras and an ultrasonic sensor. And by using a two-camera setup, our algorithm can calculate the distance of objects from the user. Additionally, the two-camera setup will also help fight off any lighting distortions. The use of an ultrasonic sensor is optional, but can be used to detect the distance of objects directly in front of the user.
Group responsibilities. Jose had the dataset, voice recognition, TTS. Enrique had distance detection, object, tracking, matching. Myself, I had voice recognition slash TTS. Eduardo had object tracking slash training data.
After collecting all the data and completing the annotation phase, we divided our data set into three categories. 86% of the data set went to training, while 9% went to validation, and finally 5% went to testing. Here are some images of our data set after being trained with YOLO V5.
Next, we will talk about how object tracking and object distance detection was possible. Before we begin, there's a couple things that we have to do. First, we have to make sure that the cameras are aligned properly. Here is a picture of the two cameras that we were using. The goal here was to align the cameras as much as possible in the X direction. Here you can see that I used the back of my ceiling and try to match it up as much as possible. The next thing that we had to do was calibrate the cameras. The reason why we had to calibrate the cameras is because even if the cameras are the same make and model and coming from the same manufacturer, there can still be some small differences in between them. And in order to get rid of any distortions, we had to calibrate the cameras. The way we did this was by using a checkerboard, which you see right there on the iPad, and we took several different pictures at different angles, making sure that the checkerboard was in the frame the entire time. We moved the checkerboard around until we were happy with the pictures that we had captured. Once we had done that, we were ready to start tracking. Here you see two frames from two different cameras. Each one is tracking me independently. In order to determine the distance of the objects, first we had to figure out where those objects appeared in each camera. The way we accomplished this was by first cropping out the object in camera 1. Next, we compared the cropped object to the frame in camera 2. We looked for key features. Once the key features were identified, we knew that the two objects were the same. After that, we were able to use triangulation to determine the distance of the object. Since each camera is giving each of their objects a unique ID independently of one another, once we figured out an object from camera 1 was the same as the object in camera 2, we were able to relate the IDs. This means that the next time we had to determine the distance of this object, we don't have to go through the whole process of feature matching to try to figure out if it's the same object or not. By doing this, we were also able to reduce computational power to ensure that the program would run as smooth as possible. In the next slide, we will go ahead and show you a quick demonstration of our project. You will see that the object is given an ID. You will also see that at the center of the object, there will be a black dot. That represents the current frame of where the object is at. A green dot represents where the object is expected to be in the next frame. Once the object approaches the camera, a voice notification will be outputted through the speakers, telling the user that an object is approaching.
Person detected.
To conclude, throughout this project, we have gained experience in collaborating, implementing features, coding standards, adapting, and revising a complex artificial intelligence project.